Now we're going to talk about different types of solids. Solids can be crystalline, and by that we mean that they have a well-ordered array of atoms or molecules. There's a long-range order to the particles in a crystalline solid. Or they can be amorphous. A is a prefix that means without. So amorphous means without shape. So an amorphous solid has no long-range order. Examples of amorphous solids are like rubber and glass. They have no particular order to their molecules or their atoms. We can take that group of crystalline solids and divide it into three different categories: molecular, ionic, and atomic. And those divisions are based on the individual units that compose the solid. So here's a table from your book. Crystalline solids. Molecular solids contain molecules. Ionic solids contain ions, cations and anions. Atomic solids contain atoms. Aren't those nice descriptive terms? Molecular solids tend to have low melting points. Ionic solids tend to have high melting points. And atomic solids, their melting points vary. Some of them are high, some of them are low. So let's look at these individually. So a molecular solid has molecules as the individual units. What holds those molecules together? What we just learned about, intermolecular forces. The dispersion forces, dipole-dipole forces, hydrogen bonding. Depends on what kind of molecules you have. Examples of molecular solids are ice, which is solid water, and dry ice, which is solid carbon dioxide. So the ice, regular ice, solid water, is held together by hydrogen bonds, and dry ice is held together by dispersion forces, because CO2 is a nonpolar molecule, which you may not get just looking at its formula, but if we look at the Lewis structure, then we see that yes, it is. Because here's carbon with its octet fulfilled by these 4 bonds, no lone pairs. And we have 2 oxygen atoms. Those are the same. And so this is a, lost the word, symmetrical, that's the word, a symmetrical molecule. So because it's not polar, carbon dioxide only has dispersion forces that are weak. And here we see that dry ice, it doesn't actually melt, it sublimes at -78. It goes directly into the gas state. Whereas ice that has hydrogen bonding, much stronger forces, melts at 0 degrees Celsius. Ionic solids, we don't say that they have molecules, we say they have formula units. And by formula unit, we mean the smallest electrically neutral collection of ions. But I think we can just say that ionic solids are composed of ions and be okay with that. Examples are table salt, calcium fluoride. We look at these compounds, they have a metal in them. When we learn to name things, we divided things into ionic and acid and covalent molecular compounds. So ionic compounds form ionic solids. These are held together by the electrostatic attractions between cations and anions, which is exactly the same as ionic bonds. Ionic bonds tend to be very, very strong. So in a piece of sodium chloride, you've got sodium atoms, sodium ions, sodium cations, chloride anions, held together in a 3-dimensional array. It just goes on and on and on. So essentially you could think of the whole thing as being one molecule. There aren't any intermolecular forces because there's only one big molecule. It's the same. And it's all held together with ionic bonds. So ionic compounds, ionic solids tend to have really high melting points because those ionic bonds are really strong. Sodium chloride melts at 801 degrees Celsius. That's pretty hot. Okay, really hard to melt table salt. Atomic solids are going to have individual atoms. So atomic solids, by definition, have to be elements. Because if you have more than one element in a compound, you're going to have either molecules or ions. So atomic solids have atoms. Examples are diamond, iron, all the metals, solid xenon. These are all atomic solids. And these can be divided into 3 more categories depending on what force is holding those atoms together. The melting points of atomic solids vary widely. So here's taking one of those groups from the previous picture, the atomic solids, and that can be divided into 3 groups. Covalent atomic solids are held together by covalent bonds. They tend to have high melting points. An example would be silicon. The silicon atoms are actually covalently bonded together. And we also have non-bonding atomic solids. These are only held together by intermolecular forces, and the only one atoms have is dispersion forces. So these are going to have very low melting points. Solid xenon is an example, but that is a solid only at very, very low temperatures. And then we have metallic atomic solids. These are held together by metallic bonds, and these have varying melting points. So we look on the periodic table, and what's one of the odd things about mercury? What is mercury's physical state at room temperature? It's a liquid. That's not usual for metals, is it? Most metals are solids. So mercury has a low melting point. It melts below room temperature. Whereas most of the other metals, you have to get them pretty hot to melt them. Like iron doesn't melt very easily. Aluminum doesn't melt very easily. They wouldn't be very useful in pans if they did, cooking pots and pans. So the atomic solids are held together by covalent bonds, covalent atomic solids. An example is diamond. Each carbon atom forms 4 covalent bonds to 4 other carbon atoms. And so the whole thing is covalently bonded together. Covalent bonds are really strong compared to intermolecular forces. A diamond crystal is really just one giant molecule. And these are going to have high melting points. Diamonds are estimated to melt at about 3,800 degrees Celsius. That's crazy hot. So if you threw your diamond into a fire, would it melt? No. Really nothing would happen to it. So like if your house burned down and you had diamonds in there, you'd have to sift through the rubble to find them, but they should be unscathed. They might be dirty, but you could wash them off and they'd be just fine. They're pretty indestructible. So here's an example of the structure of a diamond. So individual carbon atoms, and they're arranged in a very geometrical arrangement, this hexagonal pattern, and this pattern goes on and on and on throughout the whole crystal. And that's part of what makes diamonds so beautiful, is you can cut them along these lines and they get these nice faces. Non-bonding atomic solids are held together by dispersion forces. An example is xenon. Xenon doesn't form covalent bonds with other xenon atoms because it's a noble gas. These have very low melting points. Melts at minus 112. So you're not going to just run into any non-bonding atomic solids at room temperature. Metallic atomic solids are held together by metallic bonds. Metallic bonds are kind of hard to understand, and so we're just going to give you a hint about them and then not worry about it too much. The simplest model talks about positively charged ions in a sea of electrons. Iron is an example, and these metallic atomic solids, like I said, have variable melting points. Mercury melts at minus 39, but iron melts at 1809. So the melting points are kind of all over the place. Here's a picture, an illustration of the electron sea model of metallic bonds. We know that metal atoms tend to form cations, right? They tend to give up their valence electrons to form cations. So what happens when you just have metal ions? They're wanting to form these cations with a more stable electron configuration. So let's pretend this is sodium. Sodium tends to lose 1 electron. And this one loses 1 electron. And that one loses 1 electron. What's going to hold these charged things together? The cations themselves are repelled by each other. But the electrons are there as well. The electrons can't just leave, but the electrons are free to move around. I think of this as these are houses in a neighborhood. You know how blocks are laid out, and these are the houses. And the electrons are the little boys, and the moms just sent them out to play. Go outside and play. You're bothering me. Go outside and play. And so the little boys, they run all over the neighborhood, don't they? Like little wild things. They run around. But there's an attraction between this sea of electrons and these positive cations, and that's what holds them together. And this model also explains how metals conduct electricity, because these electrons are free to move. So if you put electrons in here, electrons will move, and you can pull them out the other side, and that's how metals conduct electricity. So let's identify each of these solids as being molecular, ionic, or atomic. So we just need to look at the formula and see what kind of a compound or atom or element it is. So NH3, is this ionic? No. The first element is nitrogen. The second one is hydrogen. We have two nonmetals. It's not ionic. So this forms, it's not an ionic solid. It's going to be a molecular solid. So that's a molecular solid. How about letter B? This is ionic. Here we have metal, nonmetal. When we learned how to name things, we learned to identify that as an ionic compound, and so it makes an ionic solid. How about this last one, krypton? Atomic. The atomic solids will always be individual elements. It has to be. That's the only way you have individual atoms. That wasn't a very good M. Any questions?